Chapter 1 is an introduction to chemistry. I'm going to assume that there are some of you in this class who have never taken a chemistry class before. And so if you've done some chemistry before and some of this is boring to you, my apologies. But I'm speaking to those who are brand new to chemistry. So just a little bit of history. Excuse me. I think ever since man existed, we have wondered about the things around us. And why does rain fall from the sky? And why does fire burn you? And various things like that. Humans by nature are very curious. And it's a little bit interesting to think back about thoughts that humans have had. Way back during the Greek civilization, they believed in 4 basic elements: earth, air, fire, and water. And they felt that all substances were composed of these 4 basic elements. Well, we recognize now that that's pretty ridiculous, but these people didn't have electricity. They just didn't have a lot of stuff. They didn't know very much, and they were mostly just looking at what was around them and thinking about it. These were philosophers. They thought about stuff. They were not scientists. Science is a methodical exploration of nature. We have a way of thinking about things that leads to conclusions. So we're using logical explanations to explain our observations. When we investigate scientifically, we plan our investigation. We just don't do things willy-nilly. We set out with a purpose, and this is what we're going to try to do. We carefully record our observations. When you take 1A, you will have a lab notebook, and you will record your observations in your notebook. We gather data. Data can include observations. It can include measurements. And then we look at the results of our experiments and our investigations. We look for patterns. We try to organize things. We try to figure out what it means. So the scientific method is an important concept. This is a method. It's not a series of rigid steps, but it's a general approach to investigating scientifically. So we propose an explanation for the results of an experiment in the form of a general principle. And that initial tentative proposal is called a hypothesis. So you observe something happening, and you think about it, and you say, well, I think this is what's going on. That's the hypothesis. It's not a random guess, but it's a thoughtful guess or a thoughtful proposal of what's going on. We don't stop there at the hypothesis, though. We investigate further. Further investigation may support the hypothesis. It may disprove the hypothesis. We may just have to reject it and say, well, that was a crazy idea. Or the hypothesis can be elevated to the status of a scientific principle. So basically, the scientific method follows this pattern. We ask a question. Can somebody think of a scientific question that could be investigated? What's the weight of an atom? How much does an atom weigh? Okay, that's going to be a challenging one, but that's a great question. The next step is to construct a hypothesis. That's a great example, but I think it's going to be tough for a very basic scientific method thing. So I'll throw something out there. One of the things I've noticed is that when you put helium balloons on the mailbox when you're having a party, the dark colored ones are always the ones that pop. Have you ever noticed that? Seriously, yeah, seriously. Hey, I'm a chemist, right? I notice weird things. So the question is, why do the dark balloons pop? You know, maybe you've got purple balloons and you've got light pink balloons. And it's the purple ones that keep popping, and you keep replacing them and they keep popping, and the pink ones are fine. Why? Why is it the purple ones? We can construct a hypothesis.
Oh, I know.
Yeah. So my hypothesis, as a person who understands more science than the average person, might be that the dark color of the balloon is absorbing more heat from the sun, and the balloon is getting hotter. The dark purple balloon is getting hotter than the pale pink balloon. And when balloons get hot, they expand. And if they expand too much, they pop. Is this something that we can test? Yeah, it is. So we test our hypothesis with an experiment. The experiment might be we fill up a whole bunch of balloons of all kinds of different colors. Black and dark brown and white and yellow, light colors and dark colors, and see if this is consistent that the dark colored balloons pop first and the light colored balloons last longer. If that's the case, then that supports our hypothesis that it's the dark color. There are other things we could also investigate. Maybe it's the dye in the balloon that makes it purple that weakens the latex. And it's not actually that it's getting hotter from the sun. And so then maybe we could cover it with something light colored so that we take that element out of it. I don't want to go too far, because I could go just crazy with that, as you can probably tell. But this is the idea of coming up with an idea. I think this is what's happening and why, and then how can I test it? So we test it with experiments, and then we look at the results. Sometimes the results agree with our hypothesis, with what we think is going on. Other times they don't. If they don't agree, then we may need to revise our hypothesis based on this new information. And so what happens with the scientific method is we often go around in circles, sometimes for years, going around in circles, trying to figure out this problem. But this is very different than the philosophical method that the Greeks used, where they sat around and thought about stuff and discussed it. They didn't actually do any experiments. In modern science, we test our ideas. From our results, we formulate a conclusion. Yeah, it's the dark color of the balloon that causes it to pop. Another observation we could make is, well, let's observe these balloons on a day when the sun isn't shining, because that would take the dark color. Because I think we all know that if you go out in the sun wearing a black shirt, you're going to be really hot this time of year, right? And if you wear a white shirt, you're not going to be as hot, because the white shirt reflects the heat better than the black shirt. So that's what's going on with those balloons. So if we do it on a cloudy day, would we expect the purple balloons to pop? No, because if there's no direct sunlight beaming down on them, then the color isn't going to matter. So we can investigate different aspects of this, and we go around and around with expanding our hypothesis and testing with experiment and analyzing the results. So one person can apply the scientific method and come up with a conclusion. Scientists tend to be very skeptical people. The hypothesis then, and it's important to understand the difference between hypothesis, theory, and law. A hypothesis is a tentative explanation, and we're going to test that through experimentation. So my scientist friend, may see me doing this, and I've come up with this conclusion, and I share it with him, and he's like, I don't know, I'm going to try it too. And we see something that somebody else did as a scientist, and we're like, let's see if I can reproduce that. And so other people, other scientists will try the same thing. That's one of the reasons we publish things in journals. We put that information out there, and then other scientists try to reproduce our work. When you have a theory that has been tested by many people, a hypothesis that's tested by many people, it becomes established and rises to the status of a theory. Now, in everyday life, we often dismiss things. Oh, that's just a theory. In science, a theory is a big deal. This is an explanation of general principles that has considerable evidence or facts to support it. This isn't just somebody thinking about it. A theory is something that has been tested many times and appears to be correct. There are also scientific laws. A law is just a statement of natural phenomena, with no known exceptions. So the law of gravity is probably one you're familiar with. So what's going to happen if I let go of this stylus that I'm holding up in the air? It's going to fall. Yep, look at that. Does that every time. Did somebody pick that up from me? It went way too far. I usually do it with a pen that I don't need. The law of gravity says that if something is raised above the surface of the earth and you let it go, it's going to fall down. The law of gravity does not say why that happens. Scientists are still trying to figure out exactly what gravity is. We know what it does, but we're not sure why it does that. A law says what happens. A theory explains why. Now, an interesting thing about science is that we cannot prove anything to be true. We can only prove things to be false. So a theory is what we believe to be true, but future information may show that that theory was incorrect. This is an interesting quote from Albert Einstein. "No amount of experimentation can ever prove me right. A single experiment can prove me wrong." So that's another important idea about science in general. We can support a theory. Nobody's been able to disprove it, but that doesn't mean that it is true. It's just what we believe to be true. So after a lot of testing and evidence, the hypothesis becomes a theory. The natural law is a statement of what happens. It generally involves something measurable. So experiments, initial observations, leads to a hypothesis. The hypothesis, just stating what happens, can become a natural law. If it's explaining why that happens, it becomes a theory. Theory says why, law says what. So let me write that on here. So theory, oh, that's really awful. Theory explains why. The law just says what happens. It doesn't explain why. So important difference between law and theory. Chemistry is a branch of science. The scientific method applies to all branches of science. But chemistry studies the composition of matter and its properties. So we're concerned with the properties of matter. There are many branches of chemistry. The three biggest categories are here: organic chemistry, inorganic chemistry, and biochemistry. Organic chemistry does not have to do with organic food or organic farming. In chemistry, organic means that it contains carbon. So that is traditionally a second-year course that you take after you take a full year of general chemistry. Inorganic chemistry studies all the other compounds that don't contain carbon. And then biochemistry looks at the substances derived from plants and animals and may also go into the chemical reactions that occur in biological systems. Understanding chemistry is very important. I personally believe that every educated person should have some knowledge of chemistry because it does impact our everyday lives. There are career opportunities in chemistry. There are topics of interest. You know, what's with the trans fat stuff? What does that mean? What is a trans fat? That's chemistry. Relevance to your daily life. Concern about pesticides in your foods, chemicals in your laundry soap, various things like that. There are fun experiments that we do in chemistry. Now, we're not going to do any experiments in this class because it's not a lab class, but you'll get to do some fun stuff in Chem 1A. Chemistry benefits society. Development of plastics, new kinds of textiles, gasoline additives that reduce pollution. It just goes on and on and on. Drugs all come about because of chemistry. There's chemistry. Biomedical applications, testing for various diseases, treatments of cancer, all those sorts of things involve chemistry. So here's a summary of the chapter. Scientists use the scientific method to investigate the world. Experiments lead to hypotheses, which may lead to a scientific theory. There are many more hypotheses than there are theories, because a lot of them just go by the wayside. It can lead to a theory or a law. Chemistry is often called the central science. It's got its fingers in everything. Chemistry overlaps with physics and geology and biology and medicine and everything, because all matter contains atoms, and chemists are the ones who study what atoms do. And then the impact of chemistry is felt in our everyday lives. So that's chapter 1.